Good morning everyone. Today I am going to explain the signal processing demonstration which is called two-tone sampling and sign reconstruction as you guys can see on the screen. So this demonstrations helps us to understand an important concept in signal processing called the Nyquist sampling theorem. It shows what happens when a sample signal at different sampling frequencies. In this simulation, we have a signal containing two different frequencies. The first frequency f1 is 8 Hz and the second frequency f2 is 18 Hz. So the highest frequency present in our signal is f max equals to 18 Hz. According to Nyquist sampling theorem, the sampling frequency must be at least twice the highest frequency of the signal for proper reconstruction. Therefore, Nyquist frequency equals to 2f max equals to 2 into 18 equals to 18 Hz. The simulation has a duration of 0.45 seconds and it compares three different sampling frequencies. First one is 45 Hz above Nyquist, 36 Hz at Nyquist and 27 Hz below Nyquist. Now let us look at each case. AVAP Nyquist sampling frequency 25 Hz. Okay, first we have the AVAP Nyquist case. Here the sampling frequency is 45 Hz. Our Nyquist requirement is 36 Hz, so 45 greater than 63 Hz. Therefore, the sampling frequency is sufficiently high. The simulation takes 21 samples during 0.45 second interval. If you look at the time domain graph, the blue curve represents the original signal. The red dots represent the samples taken from the signal and the green curve represents the signal reconstructed using the sync reconstruction. Here the green reconstruction follows the original blue signal quite closely. This means that the original signal can be recovered accurately from the samples. Now let us look at the frequency domain graph. We can see the frequency components of the signal since the sampling frequency is greater than twice the greatest frequency. The different frequency components can be represented without overlapping in a way that causes aliasing. So this is a good example of proper sampling. Then point number 2, at Nyquist sampling frequency equals to 36 Hz. Now we come to the second case at Nyquist. Here Fs equals to 36 Hz. Now our Nyquist requirement is also to F max equals to 36 Hz. Therefore, Fs equals to 2f max. This is exactly the Nyquist limit. The simulation takes 71 samples. Looking at the time duration graph, we have seen that there are fewer samples than in the previous case. The red dots still contain information about the original signal and the green curve uh, attempts to reconstruct the original blue graph. At the Nyquist rate, an ideal band limited signal can theoretically be reconstructed. However, this is the minimum theoretical sampling rate, so there is no extra safety margin. This is why in practical system we generally sample above the Nyquist rate rather than exactly at it. The frequency domain graph also shows that the signal is right at the limit where the frequency components can still be represented without violating the Nyquist condition. Now we will come to the point number 3, that is sampling frequency equals to 27 Hz. Finally, we have the below Nyquist case. Here Fs equals to 27 Hz, but our required sampling frequency is 36 Hz. Therefore, 27 greater less than 36. So the signal is being sampled below the Nyquist rate. Only 13 samples are taken during 0.45 second interval. Now if we look at the time domain graph, we can clearly see that the green reconstructed signal doesn't purely follow the original blue signal. This happens because there are enough samples to represent all the details of the original signal. The more okay We can see the effect of this in the frequency domain graph. So once aliasing has occurred during the sampling, we cannot simply use reconstruction to recover the original signal perfectly. So the main message of the demonstration is to accurately reconstruct a band limited signal. The sampling frequency must be at the least twice the highest frequency present in that signal. Thank you for all.